Hello, everybody. I am almost certain that you've seen some sci-fi movie where a robot performs an autonomous surgery and does so flawlessly. And you've probably thought to yourself, that's at least a couple centuries away, right? Wrong. What if I told you that the technology for that future is already in the operating rooms, watching and learning? Today, we'll be talking about a field that makes this all possible, medical computer vision. My name is Abishua Johnson, and I'm a CariSurg scholar from Jamaica. I'm a recent graduate of computer science from the University of the West Indies, Mona, and here's my CariSurg research project in a nutshell. Let's get into it. So my entire project was under the theme optical flow and key point tracking for surgical applications. Sounds like a lot? Trust me, I know. So let's start by breaking it down. To understand what optical flow and key point tracking are, we first have to understand what tracking means, generally. So let's read the definitions that we have here on the screen. And let me get my glasses for this one. We have tracking is the process of establishing correspondences between points across video frames to follow their motion through time. Now, to paint a better picture of this, I want you guys to imagine me eating a mango. Imagine looking at a video of me eating a mango. And we take two frames at different points in time, right? Some pixel in the first frame has a corresponding pixel in the second frame, right? That is what we call a correspondence. And by examining the change in the points or pixels, we can see how they have moved. And that essentially is what tracking is. Now, tracking can be performed in two different ways, and the difference lies in the number of points that we are tracking, right? So we have optical flow and key point tracking. Optical flow estimates dense motion fields by computing pixel-wise displacement vectors between consecutive frames. Essentially, what we're saying is that we're creating correspondences for every single pixel in that frame, in that video. Key point tracking, on the other hand, identifies and matches distinctive sparse feature points across frames. With key point tracking, we're only looking at specific points. So we're not tracking everything. We're only tracking specific points. For key point tracking, this entire grid here would represent a video frame, right? And those shaded regions would represent the key points. As these key points move over time, the algorithms are meant to track their position in the frame. Similarly, for optical flow, this grid is the entire frame, and what we're doing is we're tracking everything. Look at that. I like to think of key point tracking and optical flow algorithms as different families, right? Because every single algorithm, tracking algorithm that is, has to fall in one of those two groups. And now that I've given you this context, I have a question for you. Which family, which type of algorithm do you think is better? If you said key point tracking algorithms, you are absolutely incorrect. But if you said optical flow, you're still wrong. And here's why. We cannot generally say that one family is better than the other because the context is important. We have to know why we are tracking. We have to know what we are tracking. We have to know where we are tracking. So the context is important, and then we can select the best suited family of algorithms to perform the tracking. But in order to select the best suited algorithm, we have to know where they excel. So let's look at advantages and disadvantages of sparse and dense methods, or key point tracking and optical flow methods. Let's look at dense or optical flow methods. They provide complete spatial coverage because, as we said, they're tracking every single pixel. They also excel in low texture regions, so think of flat surfaces like tables or a whiteboard, and they're also robust to deformable surfaces, so think of things that can bend and stretch. Key point tracking or sparse algorithms, on the other hand, they are computationally efficient because they're not looking at every single pixel. They also provide high precision on salient or key features, and they're ideal for low resource settings and can typically be run on your simple computer, your simple GPU. For disadvantages, on the other hand, optical flow methods are computationally expensive. And what do we mean by that? We mean they usually take a longer time to track because we are tracking every single pixel. On that same point, they're also memory intensive because we have to store the correspondences for every single pixel in that video frame. And you can see how that can grow and scale depending on the length of the video. And they're also sensitive to light changes in the videos and can get confused. Key point tracking or sparse methods, they have limited spatial coverage, again, because they're not tracking every single pixel. They give poor accuracy on smooth surfaces and they are feature dependent. So the accuracy is completely dependent on those points that we are tracking or those features. Now, given the advantages and disadvantages of both, I want you guys to tell me which family do you think is better for the surgical context? You probably thought optical flow, right? And I get it. But again, it still depends on what is important in the surgical context. What are the things that we need from these tracking algorithms? And those two things that are required for the surgical context is or are accuracy and speed. Now, based on the advantages and disadvantages that we got, it seems that key point tracking is usually faster than optical flow. So if we're really looking for speed, key point tracking algorithms would be better, right? Then we also established that optical flow algorithms might be better in terms of accuracy because the surgical context comprises a lot of deformable, smooth, textureless features. So optical flow algorithms would perform better in terms of accuracy. So you see, the problem that we have here is that we have two different ends of extremes with an accuracy speed trade-off. And that brings us to my big question and the thing that motivated my research. We want to create a new family of algorithms that allows us to traverse this accuracy speed spectrum. So the big question is, can we develop a sparse dense approach to provide practical solutions along that accuracy speed spectrum, essentially making the most of the best of the both worlds? So how do we go about doing this? Let's look at our methodology. The first step in any research is establishing a baseline. We need to know where we stand with the current state of the art. So what I did was I set up a fair comparison between the two families of algorithms. And the first step is model selection. We selected four baseline models representing both families, two optical flow methods and two key point tracking methods, two dense methods and two sparse methods. Then we moved to model evaluation. We evaluated out-of-box performance on the STIR dataset so that we could compare the models on common ground. Essentially, we take the four models and we evaluate their performance with the same setup to see how best they are performing. The STIR Challenge 2024 dataset comprises of 60 surgical video sequences labeled using infrared fluorescent markers. The dataset contains 496 labeled tracking points. So the STIR dataset, it provides us with data that we can use, that we can run the different selected models on so that we can evaluate the performance. And that data set, let me give you guys a glimpse of it. It provides us with frames and video sequences, right? And the frames, what they did was they marked them using fluorescent dye, and then they converted them to binary images, which is just a black background with the fluorescent markers represented as the white blotches that you're seeing here. And what that allows us to do now is provide ground truth data of starting points and endpoints of video sequences, right? So how do we evaluate? How do we use the models to evaluate the performance? The first step is loading the pre-trained models. So we took the four selected models and we loaded them into a coding environment so that we would be able to actually run them. Then we input start points and the video sequences. Then we have the model track the movement of the marked key points across the different video frames. And then we have the model actually predict what the final endpoint would be. And based on how fast and how accurate those predictions are, we would have evaluated the performance. Now, the different classes of metrics that we looked at were accuracy and speed. And under accuracy, we calculated mean endpoint error, and that is just the average pixel distance between the predicted points and the ground truth endpoints. So based on how close these figures are, we can essentially, understand how accurate the model is predicting, right? And the lower this value is, the better. Then we looked at the accuracy at thresholds, and this is the percentage of predictions within acceptable distance ranges. So we understand that there might be some, you know, error, right? And so we create a boundary, let's say 16 pixels, and we say if the model predicts the point within that range, if the predicted value is within 16 pixels of the actual endpoint, then we count it as correct. And the higher this figure is, the higher the percentage of predictions within those acceptable ranges are, the better the model is performing. In terms of speed, we looked at runtime, which is just the computational time for the model to run on the entire STIR dataset, and the inference time, which is computational time per frame, excluding any input or output and pre-processing. Right. So, given all of this, let's look at the results that we got back. For mean endpoint error, which we've already established that the lower that value is, the better the model is performing, we see that in this bar chart, we see that the dense methods are performing better than the sparse methods, with MFT having a mean endpoint error of 15.26 pixels and superglue having a mean endpoint error of 78.92 pixels. For our accuracy at thresholds, we see that within a 16 pixel threshold, or dense models again are outperforming our sparse models, with MFT leading and co-tracker and superpoint glue hanging behind. In terms of runtime, on the other hand, we see our sparse models actually outperforming our dense models, with SuperPoint, SuperGLUE, and CodeTracker having around the same runtime and MFT running in about an hour on the STIR dataset. So this confirms our initial hypothesis, what we've already seen in our research, that optical flow methods are usually more accurate in the surgical context, and sparse methods or key point tracking methods are usually faster. Right. So where does this leave us? How do we come up with an approach that essentially takes advantage of the best of both worlds? The solution, Keypoint inspired optical flow algorithms. So this is a new family of algorithms that perform optical flow in a keypoint driven manner where specific points of interest guide the computation rather than processing the entire frame uniformly. So this is a new family that we've come up with, right? If you remember, what we're trying to do here is create some sort of hybrid approach that allows us to take advantage of the accuracy from optical flow and the speed from key point tracking, and then allow us to traverse that spectrum. So what we did was we took one family and we tried to make it more like the other. Let me explain. We took MFT, or best performing optical flow model, and we tried to speed it up. So we have to think about the reason why key point tracking algorithms are fast. And that reason, we would have discussed this at the start of the video, I believe, is because in key point tracking, they're not tracking every single pixel. In optical flow, they're treating every pixel uniformly. But if we can only allocate our optical flow model a specific portion of the video frame, then hypothetically, we could significantly speed up the time at which it processes the frames in the video sequence. Hence, Keypoint inspired, because we're taking that inspiration of not processing every single pixel, but only specific points. However, in this case, we are applying it more intelligently. I don't want you guys to get confused. So this is not merely key point tracking. It doesn't converge to key point tracking. It's still optical flow. It's just that we're applying optical flow in a manner that is like key point. You would have seen in the definition here, key point driven manner. So we're drawing inspiration from the fact that in key point, we're not tracking everything, and taking that kind of idea and using optical flow to do the same essentially. So what we did was we came up with two approaches, and we can learn more about this here. We came up with two approaches, patch tracker and shrink tracker. So this is how patch tracker works. So we're given some video sequence and we have our initial key points. The first thing that we do is we create a bounding box that incorporates every single point in the initial frame. This bounding box is called a minimum bounding box. We take the leftmost point, rightmost point, topmost, and bottommost point so that we can form that box. And we add a little safety margin just in case it falls outside of the first bounding box. And then we round it off so that it is a square. I know that this doesn't look like a square, but think of it as one. And then finally, we run MFT on that bounded box. And then as the points move, we recreate the patch again and run the entire process again. So this is what we call an adaptive patch, because the patch doesn't merely stay static, but it reforms based on the movements of the points. And we see in this that the number of pixels that we're tracking, they've significantly decreased because we're not tracking everything. I think this is a perfect portrayal of how the algorithm works. Why? Because you can clearly see points that are not tracked here, and then when the patch adapts, you see that these points are not tracked, these pixels are not tracked as well. So this significantly decreases the number of pixels that we track by simply, being intelligent about how and where we apply our optical flow model. Okay, let's now look at shrink tracker. Now this one is a bit simpler than path tracker in that all we're doing is we're downsampling, downsizing the original frame. So right, we take our original frame and we size it down by some scale factor. So we take the original frame with its original resolution and we downsize it by some scale factor, thereby significantly decreasing the number of pixels, right? And we track our key points as normal with our optical flow model in this downsampled state. And then when the final endpoints are predicted, we map it back and upsize it to the original frame. So very, very simple. And you'll see here too that by downsizing the image or the frames, what we're doing is we're decreasing the number of pixels and then running MFT on that decreased frame. And that would be our two approaches. But I guess the big question is whether it worked or not. So let's take a quick look at our results. So if you look at tracking accuracy at the different thresholds, you will see that MFT is still the best performing in terms of accuracy. But right below MFT, we actually have our scaled tracker and our path tracker. So the two new family of algorithms, or rather the two algorithms that belong to the new family that we created, sit in between MFT and Raft, right where we want it. So it is outperforming all our key point tracking algorithms and even outperforming one of our optical flow algorithms. And it's sitting right below MFT. If we look at our mean endpoint error, we see here too where our scale tracker and our path tracker actually sit right in between MFT and RAF, meaning that they are performing better than not only our key point tracking algorithms, but one of our optical flow. So it's a good sign. It's a good sign. And then in terms of runtime, we actually see our models or new algorithms rather, path tracker, performing better than all the other algorithms and our scale tracker outperforming MFT, so still right where we want it. So I would say that they performed reasonably well given the circumstances. So how do we actually apply our key point inspired optical flow algorithms to a surgical context for surgical applications? So we know that KIOFA works on the STIR benchmark, but benchmarks are benchmarks. The real question is, does this generalize to actual clinical use cases? And that's what we're going to be looking at. So here's the setup. We're going to be using our KIOFAs on the Jigsaw dataset. Now, the Jigsaw dataset comprises surgical training videos of not time tasks, among other things, labeled by expertise. So we have expert, intermediate, and novice categories, right? What we did was we selected two categories, or two videos rather, from each category, 6 videos in total, right? And the metric that we'll be working with is the smoothness of motion. Then we used a Kiofa tracker, most notably one of our PAT trackers, to extract tool trajectories from the 2D video frames. So we manually initialize the tracking points on the surgical instrument tips in the first frame, and then we let PAT tracker track them across the first 200 frames. And then that output would give us a 2D trajectory path showing how each surgeon moved their tools. And the question here is, can motion tracking reveal the difference between a seasoned surgeon and someone who just picked up the tool yesterday? So let's look at our results. As you can see here, the motion clearly tells a story. This is the 2D trajectory plot of an expert. And when you look at this, you can see smooth, controlled, direct movements. The paths look like they were drawn with intention, with minimal corrections. We have efficient use of the workspace happening here. These surgeons know exactly where they're going before they move. Look at these paths. They're smooth, direct, and intentional. Compare that now to an intermediate. It's almost a mix of the both. Some segments look expert-like with smooth motions if we look at here and here and here, but others show hesitation or correction of the course. You can see the skill developing here, right? It's there, but it's not there yet. In our novice trajectory plot now, we can see that the movement is a bit more erratic, a bit more exploratory, right? Lots of back and forth happening, reversals and wait, that's not right type of movements. That's what we're seeing here. So yeah, these trajectories in this specific plot look like someone was solving a maze by trial and error. But what we see coming out from this, though, what this means is that Kiofa can extract motion signatures that correlate with surgical skill. The visual difference is it's striking, right? You don't need a trained eye to spot the difference between the expert and the novice trajectories. They look fundamentally different. Yeah, so let's just look really quickly at some limitations and then we can wrap up with our conclusion. I would say the biggest limitation of this entire project is probably one, the reliance on MFT, and two, it's only based off the STIR dataset. So we only tested the models as well as Kiofa on the STIR surgical dataset. So yeah, we know that a real operating room would have, a lot more unpredictable things happening. The STIR dataset was a controlled type of dataset. So it might not accurately to the fullest extent reflect what an actual operating room would be like. Right. And yeah, so what's the takeaway from all of this? You don't have to choose between accuracy and speed. With the right approach, we can track more intelligently so that we can get the best of both worlds. Now, this video is just the tip of the iceberg. I hope that I was able to break it down very simply and plainly. For a more extensive type of review of the work that was conducted here, I would advise you guys to read my paper. Okay, and I'm assuming that the link for that will be provided in the description below. Hopefully by the time that this video goes out, it is published. So thank you guys for tuning in to my research project, and that is a wrap. Thank you.